Now, the paper addresses one of the most pressing issues raised by cryptocurrency, namely how to provide a theory for their fundamental value. And although several papers have already studied this question, obviously, this article distinguishes itself by grounding its model in standard asset pricing theory and linking equilibrium price with the concentration in the mining industry. And I believe that's completely new and quite intriguing and interesting. Now, where does this link, sorry, one second, where does this link comes from? From this premise, this seminal idea, which is new again, that cryptocurrency can be thought of as a Lucas tree, whose fruits can be consumed all over the globe. It's really like a worldwide asset that everybody can consume. However, the production of the tree is a monopoly of miners. You have to go through miners to basically access the services of the tree. And as I already said in the presentation, you should think of miner as intermediary to access the tree. Now, I think this is, I was really struck by the idea because it's both beautiful and a natural starting point. Its main benefit is that it connects the model to a well-established tradition of asset pricing that goes back to Lucas' theory, but it also underlines the novelty of the problem raised by cryptocurrency, right? And what is new is that in a decentralized world, given the decentralized nature of crypto, miners can compete for the access to the tree. And as far as I know, this is new and has not been yet covered in the pricing literature. Once you take into account this particular feature, you get a series of findings. The first one was not much discussed in the talk, but it's interesting, I believe, is that the authors find a unique equilibrium price. And the theory paper on cryptocurrency pricing tend to outline the sunspot nature of crypto and the fact that they can be moved by animal spirits. In this model, and I will explain why later, you indeed get one equilibrium price, even when you allow for a feedback loop from services to price themselves. Now, the main insights, that is really the core of the paper, are threefold. First, mining pool concentration decreases the price of the crypto and increases its volatility. Insights that are in the last section of the paper tested against the data and with success. I'll come back to that at the end. Now, these effects are actually amplified when the services of the crypto are proportional to the price of the cryptocurrency itself. And finally, as I said again, okay, I'm repeating myself, there's a test on the data and they show that indeed mining pool concentration affects negatively the price of Bitcoin. So what I will do in that talk, because I think it's really mostly a theoretical model, I will just, maybe it's repetitive, I will, sorry, I will do again what you did, and not very creatively raise some question where I had questions, okay? It's a challenging paper, so I'm still wrapping my head around it, which is good, by the way, because I think there is a lot to understand in it. The first element, as I said, is that you have this Lucas tree and crypto are held by households just to get access to the services of the tree. So first, this is a bit abstract, right? Crypto are not held to buy stuff or per se. They are used to get access to that tree. Now, what does that tree produces? It produces a perishable good or services, Y, and the utility of, the quantity of the good is made of two components, S to the power beta and D to the power 1 minus beta. So what is S? S is the price of the crypto, and D is some exogenous utility. It's not really specified in the paper what it can be, but I guess it could be anonymity, I imagine, or this kind of services you get from crypto, right? That are really specific to Bitcoin. Or you want to pay something, you want to buy some Ether, you don't want to pay tax, I don't know, okay. But S is this feedback effect, right? That and this an idea that goes back to Tirol and has been resurrected recently by Bruno Bier and co-author, that when you look at the medium of exchange, when the value of the medium of exchange doubles, you can buy 2 times more goods, so its utility doubles. right? And when you have that, then it's well known that you get self-fulfilling prices and sunspot and all kind of equilibria. So the parameter beta calibrates, we calibrate the strength of this feedback loop. When beta is 1, we are back to the model of Bruno, essentially. And here, the only services is basically proportional to the price. So then again, you will get sunspot. But as soon as beta is inferior to 1, the price is grounded in D, the exogenous utility. And here you have unicity of the price. So that was the first thing. Maybe it should be outlined a little bit in the paper, because I was scratching my head why we don't have multiplicity and so on. And it's basically as soon as beta is inferior to 1, you get a unique equilibrium price, which is a weak condition. You just have to assume a little bit of exogenous utility, and then you get a really you get a strong prediction about the equilibrium price, which is really nice. Now, I also would like to outline that beta, although it's interesting to have it because clearly there is this feedback effect, many of the main insights don't depend on beta. You can turn off this channel. So basically assume that the good is just proportional to this exogenous variable D, and still you will get the effect of concentration on price. So maybe for the exposition, it's easier to forget about it and focus on the cases where, okay, you have this Lucas tree will produce a stream of utility, which is purely exogenous. Now, the novelty of the model up to now, nothing new. The novelty is that you have the mining pools. And here we only have 2 mining pools. This is for simplicity. So no entry and exit. This is not model. We assume there are 2 mining pools, and they share the services provided by the tree. And also what's important is that the household can only go through the pools if they want to access the tree. Okay, they are really intermediary. They are gatekeeper in a way. And the share they have from the tree is given by this parameter lambda, which is exogenous. So the model does not explain concentration. It takes it as given. What the model tries to do is the impact of concentration on prices, right? Now, given that, you have to specify the preferences of the agents. So you have 2 types of agents, the pools themselves. And what they do is that they can consume their output, C. You see, they can only consume their output. On the other hand, the household, they can consume the output of the miner, right? Again, they go through the miner, and they can consume the output of pool 1 or pool 2. And they may have like home bias preferences for one pool. But again, this is for generality. So gamma 1 can be turned off and the results still carry. Here, I think one assumption is key is this imperfect substitutability from the point of view of the household between the output of pool 1 and pool 2. In the paper, and as explained in the talk, there's this idea that you may have a home bias. You live in one country, you like better the output of one pool. It's not completely obvious why you may have imperfect substitutability. Huh? Okay, so because in the end, they are producing Bitcoin and Bitcoin are fungible, but maybe, okay, it's more easy to access some pools for whatever reason. And this is a bit not, this is taken as given, but it's really important that we have that because if we didn't have that, concentration would not matter. If they were perfect substitute, this would be irrelevant. Concentration will be irrelevant for the price. And the second thing is that, as you can see, the household consume only the flow of services generated by the pool. They don't have a stock of crypto that gives them some utility. What they get is they have a stock of crypto that gives them access to the pool, and the pool produces something, and that's where they get utility from. That's a bit abstract, okay, in a sense. So I would like maybe to read or hear more about how it relates to crypto, but that's how it's modeled. Now, here I'm going to go fast because you explained it very well. So we have the same slide, so maybe it means that we see the model in the same way. So the key things are this. So now you need to see the impact of concentration on the revenue of the miner. Okay. So the first thing is, what is the impact of concentration on the pricing rule of the miner, on the fees? So P, remember, P is the fee charged by P1 by miner mining pool 1 and P2 by mining pool 2. First, we define the numerator, which is the sum of these fees. And then you can see that when lambda 1 goes to 1, so when the pool 1 gets almost all the tree, it has to charge a lower price. Its price has to go down. And vice versa, the price of pool 2 has to go up. Why? Again, it goes to the imperfect substitutability, because one good becomes rarer, you're ready to pay more for it. If there were a perfect substitute, you will not get any of that, okay? But since one pool becomes very small, you're ready to pay a higher price for it because there is imperfect substitution between the output of both pools. Okay, now here I have a question. The choice of numeraire doesn't seem to be neutral, and I have to figure that out. Not clear to me. So what happened is that, let's say when pool 1 gets all the share, okay, lambda 1 goes to 1, then the price of the output of pool 2 converges to P bar. And so if you raise P bar, the price of pool 2 goes higher, and it has impact on the dynamic, not on the qualitative insight of the model, but on its quantitative prediction. So that's a bit puzzling why a numeraire choice is so relevant. Or maybe it's not, it's just a renormalization of all the outcome. Just an open question. So once you have that, then you have, as explained again in the talk, you have two effects. The price, let's say when lambda 1 goes to 1, the price goes to 0 for pool 1, but it produces more. So you have a quantity and a price effect. Now what you can show is that actually the price effect will dominate. So here I take the case where there is no home bias, gamma 1 equal 1. Here it's very easy to have the revenue share. It's just lambda 1 minus lambda 1 square times P bar. And you can see it's an inverted U shape. It's obvious with a peak at 1/2. So the maximum revenue share is exactly when concentration is minimized because both pools are the same size. So once you have that, I mean, that's it, because you can show that the price is proportional to the revenue share V, as you can see here. And since you have this inverted U shape between revenue share and concentration, you will also have the same relationship between concentration and cryptocurrency price. Now, I don't have much more to add, so I will come to my question. So the first thing to understand is, why is a cryptocurrency price proportional to the pool's revenue? That's the first question, because this is why the result on concentration carries over to the price of the crypto. So this comes from a no arbitrage condition, which is written here. So I forgot, this is zeta, I guess, maybe. I will call it zeta, which is a stochastic discount factor times S, the price of the crypto, is equal from the no arbitrage condition to this expectation. Why? It's a martingale representation. Why? Because remember, the cryptocurrency gives you access to the services of the pool. That's the only reason why you are holding the crypto, not to use it to buy something. You use it to get access to the pool. And what are the revenue of the pool is how much they charge times their share of the production. So actually, you can rewrite it in this way, and you see that it's proportional to the revenue share times the output of the pool. So we have seen that V converges to 0 when lambda 1 converges to 1. So of course, the price will also converge to 0. So what is the intuition between this no arbitrage condition? As I said, is that ST is a claim on all future services from the tree. Okay. And why is it true? Because in the model, households can only consume the flow of services produced by the pools. And this is a bit, okay, I mean, I still have to wrap my head around that, because you also have to admit that the crypto is storable, right? So when I hold crypto, I have crypto in my wallet, and I don't need to go through the pool. And there's some benefit you get from just having crypto independently of your interaction with the pool. So what about the utility that is derived from the stock of coin that you have accumulated and that you will use for transaction? Here we have a model where all the production is perishable in the same period, and that's the only sources of utility. So maybe here there is a connection. Maybe it doesn't matter, because maybe we could have like, it's some kind of outside good, probably actually, but I would have liked to read more about that. And finally, if I have a few more minutes, I think the key insight is why mining pool concentration is has this non-monotonic effect on mining pool revenues. And maybe here in the paper, I think I would have liked to read more intuition. And let me be clear, I'm not questioning the validity of the result. I went through the proof and it's very well explained. I'm convinced that it's correct. I'm just trying to figure out what are the key assumptions, right? So what I did, and it's a bit embarrassing actually, I don't know if I should show that. I went back, to the very simple case where takes the partial equilibrium model and you have a tree, and you split its output. Okay, and very, very, very simple. So you are at the minimum concentration, you split the output in half, and then the price is P bar divided by 2. Now it goes to lambda 1 minus lambda. So you have an increase in dispersion, an increase in concentration. Now, if you just take the inverse utility and from Jensen inequality, it's obvious that the average price will go up. All right, so I'm not saying it applies to the model. I'm just trying to see what will happen if you were to split the fruit in a tree and like pair both sides with imperfect substitutability. So now in the model, this cannot happen because remember the normalization assume that the sum of the price has to be constant and equal to P bar, which is exogenous. So is it a constraint or is it naturally justified? You see my point? So if I take just a partial equilibrium analysis, the price will go up and it cannot happen in your model. So by imposing this numeraire, you're actually requiring that the price is constant. And I was wondering, maybe is it actually an implicit constraint on your solution, or is it not? And so, since I'm convinced that your solution is correct, what I've shown here cannot happen. So what has to happen is that the Lagrange multiplier has to move. Okay, and why do they move? Because the consumption is split between, if you remember, the household and the miner, because the miner also consumes some part of the fruit. So my guess is that the miner, when their pool becomes smaller, they have less, their wealth goes down, and they are maybe less likely to consume. Okay, and that might compensate the effect. So the wealth distribution and the adjustment in the Lagrange multiplier is what makes the solution an equilibrium solution, but it's hard to understand in which direction they move. And that brings me to my last question, whether the initialization of wealth that you use is really neutral. So in the solution, you use an initialization of wealth, which is proportional to the share. And it's probably neutral, but when you do the proof, it looks like it's instrumental. And I was wondering whether it is or not, okay? And I didn't have the time to check it out. So to summarize, I would say that this question about the normalization and also the robustness, so I forgot to write it down. This graph works when you have prudence in the utility function. So what happens if your utility function does not display prudence? Then, okay, the price will remain constant because you will not have this curvature. The third derivative will remain will not be positive. And so I was wondering, maybe you should look at the effect of a prudence in the utility function for the household. Okay, so that's all I had to say. To summarize, this is an ambitious paper with fundamentally new insights. I think it will be useful I think it will have an impact on how we think about crypto, not to convey your message. Okay. I think it will be useful to build the intuition for the main result, assessing the robustness to the specification of the utility function and the choice of numeraire, and also to outline more explicitly the connection between the hypothesis and the actual structure of cryptocurrency, in particular, the fact that they are storable, right?